All right, everyone, welcome. If you're in engineering, you've definitely heard about transistors. They're the bedrock of modern electronics. But today, we're not just talking about any transistor. We're going to dive deep into a special one, the JFET, or the junction field effect transistor. My goal here is to break this down so it actually makes sense, without all the textbook jargon. So, let's get right into it.
So I want you to imagine something. Inside every single electronic device you own, your phone, your laptop, everything, there's basically a river. But it's not a river of water, it's a river of electrons. And the biggest challenge, the fundamental problem in all of electronics is how do you control that flow? How do you turn it up, turn it down, and shut it off with incredible precision? Well, the answer in concept is surprisingly simple. You build a faucet. Not a metal one, but an electronic one. A device that can control that river of electrons without ever touching it. And that, right there, is exactly what a transistor is. The JFET we're talking about today, it's a really, really clever version of that faucet. Keep that image in your head because it's going to make everything else just click into place. Okay, so in the world of transistors, there are really two big families. Now, you've probably already spent some time with the BJT, the bipolar junction transistor. Well, today, we're meeting its cousin, the FET, the field effect transistor. Now, they both do a similar job. They both control current, but the way they go about it is completely different. And this right here, this is the core difference, the most important thing to get. A BJT is current controlled. It's like using a small stream of water to control a much bigger river. But an FET, our JFET, is voltage controlled. So instead of using a current to control a current, you're using electric pressure, a voltage, to control the flow. It's a much more efficient, much more elegant way of doing things. So let's put a quick formal definition on this. A field effect transistor, the name says it all, its whole operation relies on an electric field to do the work. And here's the other key term you have to remember, unipolar. Unlike a BJT, which uses both negative electrons and positive holes, a JFET keeps it simple. It uses only one type of charge carrier to get the job done. This is a huge distinction. All right, now for the really cool part. How does this electronic faucet actually work? How can a voltage, which isn't a physical thing, literally reach in and squeeze a channel of flowing electrons? Let's zoom in and take a look under the hood. So this is what it looks like on the inside. You've got 3 terminals, 3 connections. You've got the source, that's where our river of electrons begins. You've got the drain, that's where the electrons exit. And then you have the gate. The gate is the key to everything. It is the handle on our electronic faucet. Now, we're going to walk through this operation one step at a time. Let's see exactly what happens when we start turning that knob, when we start changing the voltage on the gate. First up, let's imagine our faucet is turned all the way on. This is what happens when the voltage between the gate and the source, what we call VGS, is 0. With no controlling voltage applied, that channel is wide open and electrons flow freely from the source to the drain. This gives us the maximum possible current. So what happens when we apply a negative voltage to the gate? Well, think about it for a second. The channel is made of N-type material, which means it's full of negative electrons. What do like charges do? They repel each other, right? So that negative voltage on the gate literally pushes the electrons in the channel away from it. This creates an area with no free electrons, which we call a depletion region. It's like the walls of the channel are starting to squeeze inwards on our river. And what if we keep making that gate voltage more and more negative? You guessed it, that depletion region gets wider and wider, squeezing that channel tighter, until eventually the 2 regions touch. At that point, the channel is completely pinched off. The path is blocked. The river of electrons stops flowing. We've turned the faucet completely off, just by using an electric field. So we get the physics going on inside. But as engineers, what we really care about is how the device behaves from the outside, in a real circuit. And for that, we need to look at its VI characteristic curves. Think of these curves as the user manual for the JFET. Now, I know this graph can look a little intimidating at first, but it tells a pretty simple story. On the vertical axis, you've got the drain current. That's our electron flow. On the horizontal axis is the voltage across the device. Each of these different curves represents a different setting for our gate voltage, our faucet handle. And you can clearly see a few different regions of operation. In the beginning, the ohmic region, current rises with voltage. Then it hits the saturation region, where the current just flattens out and stays constant. And finally, if the gate voltage is negative enough, we hit the cutoff region, and the current drops to basically 0. That point where the current stops increasing and flattens out, that is a critically important point. We call it the pinch-off voltage, or VP.
This is the magic spot where the JFET stops behaving like a resistor and starts behaving like a constant current source. And that ability to provide a steady, constant current is an incredibly useful trick in circuit design.
Okay, everybody, listen up for a second. Let's switch gears and talk about what really matters. Exams. For the next couple of slides, you're going to want to pay very close attention. This is the stuff that you will almost certainly be tested on. This is your blueprint for the exam. Look at this list. These are the greatest hits of JFET exam questions. Explain the operation. We just did that. It's the electronic faucet squeezing the river. Draw and explain the VI characteristics. That's the graph we just analyzed. And comparing the JFET to a BJT, that's a classic. If you can nail these 4 points, you are in fantastic shape.
And of course, there's the math. This right here is the Shockley equation. This is the master formula. It's the equation that directly connects the output drain current ID to the controlling gate voltage, VGS. If you need to solve a numerical problem with a JFET, this is your weapon. You absolutely have to memorize this, understand what each piece means, and practice using it.
Okay, we have covered a ton of ground. So before we finish up, let's do a super fast, high-level recap of the most important things you need to walk away with today. Here it is, side by side, the main event. BJT, it's current controlled. JFET, it's voltage controlled. BJT is bipolar, using 2 types of carriers. JFET is unipolar, using only 1. And here's the big one. A JFET has an extremely high input impedance. That means it doesn't really draw any current from the circuit that's controlling it.
So why do we even care? Why would an engineer pick a JFET over a BJT? Well, there are a few huge reasons. That high input impedance makes it perfect for amplifying very weak signals without messing them up. They're also generally more stable when the temperature changes, and they're just quieter. They produce less electrical noise, which is why you find them in high-end audio equipment and sensitive scientific instruments. So we started with a simple question. How do you control a river of electrons? And we found the answer in this elegant little device, this electronic faucet we call the JFET. You now understand the principle behind it, you know its structure, and you know how it behaves. So the only question left is, now that you can control the flow, what are you going to build?